In this video, we'll calculate pH changes as we titrate. Earlier, we've looked at more stoichiometry calculations in a titration. Now we're going to put a little acid-base spin on it, and we'll look at changes in pH. We've got a titration here of a strong acid and a strong base. 25 milliliters of 0.1 molar hydrochloric acid and some sodium hydroxide. So this looks like a pretty typical titration curve for strong acid, strong base. I would expect my equivalence point to be somewhere around a pH of 7 if it's strong acid, strong base. This would be the equivalence point. We'll find out if that's about right. The first calculation we're going to do is just the initial pH of that 0.1 molar hydrochloric acid solution. Piece of cake. It's a strong acid. pH is opposite log of that hydrogen concentration, which will be exactly 0.1000 molar. How about that for sig figs, huh? There, so we'll plug in our calculator, and we will have a pH of 1 initially, which actually looks about right on the graph. It looks like it's starting at a pH of approximately 1. Makes sense? Relatively strong acid. Let's see what happens as we add base. Calculate the pH of the hydrochloric acid solution following the addition of 10 milliliters of sodium hydroxide. Random molarity, 0.1063. Okay, we'll make it work. Here's one thing that we got to do, and I would do it first. There's different options. I forget how your textbook has you do this, but I would do it first so that you don't forget. When we mix the acid and the base, we're in a sense like diluting that original acid solution. We're changing the volume, and that's going to affect the molarities. So I would do this first. We need to recalculate the molarity after we combine the solutions. So let's say I do the acid. We have to use that M1V1 equals M2V2. We can use this little equation to calculate a change in molarity as we change the volume, which is essentially what we're doing. The original molarity is 0.1000. The original volume is 25 milliliters. We want to know the new molarity, M2, when we combine these solutions and the total volume becomes 35 milliliters. So we plug it in our calculator, and it's not a big deal. That's why I would suggest doing this first, because the acid is going to change in molarity when we, in a sense, dilute it, when we add more solution. My new molarity, M2. Yeah, I don't know if I really feel like going 4 sig figs here. Forgive me. Let's go about 3.0714. I think that's going to be good enough. And then we do the same thing with the base. The base. M1V1 equals M2V2. The original molarity of the base is 0.1063. Originally, we have 10 milliliters. I want to know the new molarity when the final volume becomes 35. M2. Let's say about 0.0303. All right. Here's why I would do this first. Because number one, it's not hard. Number two, you might forget to do it later. And number three, these are the molarities that I want to put in my ice table. You could do this with moles, and then at the end you have to divide by volume, which, I don't know, it's just an extra step at the end. I would say let's just start out the ice table with the numbers that we want. We want the net ionic equation when I start this ice table, which is actually really easy for this titration. Chlorine is a spectator, and so is sodium. So when you've got a strong acid, strong base like this, your net ionic equation is actually just the hydrogen ion reacting with the hydroxide, forming water. Essentially, this goes to completion. So we'll just use a one-sided arrow. I mean, if you left in the chlorine and the sodium, your other product is sodium chloride, which is 100% aqueous. The ions are in solution, so we can leave them out. Then we set up an ice table, and we see what we got here. Eventually, we can set up an ice table. Using these new molarities, once I combine the volumes, my hydrogen is 0.0714. My hydroxide is 0.0303. Initially, I have no water. Okay, so we know that this thing is going to go forward, and I know that water is a pure liquid, but obviously we're going to form some water in this strong acid, strong base titration. So we're going to react these two as completely as possible. Essentially, this is kind of like a limiting reactant problem. Right now, the hydroxide is the limiting reactant, so we're going to get rid of it. 303. This guy's going to go down to 0. Everybody else reacts accordingly. So the hydrogen will go down by that amount. 0.303. The water would go up by that amount. 0.3. So that at equilibrium, this is about 0.0411. And then this will just be 0.0303. And these are like M for molarity, or we could kind of put an M there if we wanted to. All right, so now we got to calculate the pH. We've got two things remaining. We've got some extra hydrogen and we've got some water. I really only need to calculate the pH using the ion that's going to have a larger effect on pH, which is obviously the hydrogen. So I can ignore the water. We've got hydrogen left over, strong acid. So we can go pH equals opposite log of this hydrogen concentration, 0.0411. My pH is about 1.39. They're not bad. These strong acid, strong base titrations really do become kind of a limiting reactant situation. Which reactant is limiting excess between the hydrogen and the hydroxide will react as completely as possible, and we'll do the pH according to whatever ion remains in the solution. Let's try another one. pH, 25 milliliter sample of the 0.1 molar acid with the addition of 23.5 milliliters of that random base. Let's redo the molarities first. Acid. The original molarity is 0.1. The original volume is 25 milliliters. I want to know the new molarity, M2. When I combine volumes, so my new volume becomes 48.5 milliliters. M2. Oh, let's see. How about 0.051? Whoa. 15? That's weird. 515 molar. We'll do the same thing with the base. Let's see what we get. The base is 0.1063 molar. Originally, there's 23.5 milliliters. I want to know the new molarity at 48.5 milliliters. M2. Hey, what do you know? They're the same. 0.0515. Magic. So watch what happens when I set up this ice table. I've got my net ionic equation, hydrogen plus hydroxide, forming water. I can ICE this thing. These guys are the same, 0.0515 molar hydrogen. That's a M. That's a messy M. We can do better. There we go. M. 0.0515 molar hydroxide. Initially no water. I react these as completely as possible, which means we're going to bring them down to 0. 0 minus 0.0515. And then we're going to form some water. That's all we're going to have is water left over. Guess what? We have reached the equivalence point. The equivalence point is when I have the stoichiometric ratio from the balanced equation. I have equal moles of hydrogen and hydroxide. We are at the equivalence point. And if we look back at that original graph, the pH at the equivalence point was supposed to be 7. You got it. All we have left at the equivalence point is water. pH is 7. I don't really even need to do a calculation. I know the pH of water should be neutral at 7. That's in essence what the equivalence point is. We have equal amounts of hydrogen and hydroxide according to the balanced equation. All I have left is water. The pH really should be neutral. So that graph at the beginning wasn't a bad graph. Let's try one more. One more option. What do we got? Same acid, 30 milliliters of base. Let's redo those molarities right away. If I don't do them right away, I'm afraid I'll forget. This acid, 0.1000. Initially 25 milliliters. I want to know the new molarity, M2, when I combine volumes, which means I should have 55 milliliters. M2, 0.0455 molar. We do the same thing with the base. The original base is 0.1063 molar. Initially, I have 30 milliliters. I want to know the new molarity at 55. There we go. M2. 0.058. Let's go 0. All right, not bad. Let's do the ice table. Hydrogen plus hydroxide forms water. ICE. Initially, my hydrogen is going to be 0.0455. My hydroxide is 0.0580. No water. I can probably see where we're going with this one now. We've got extra hydroxide. Hydrogen's the limiting reactant. So we'll react this as completely as possible, meaning we'll bring hydrogen down to 0. This is going to go down by 0.0455 moles per liter. So it'll be about 0.0125. And the water is going to go up. Obviously, we're going to form some water. 0.455. I suppose we can put an M for molarity if we want. All right, so again, now we do have particles remaining in the solution. We've got extra hydroxide and we've got water. Of these two, the one that's going to have a greater effect on the pH is this guy, the hydroxide. So we do the pH of the solution based on the hydroxide. pH. Actually, let's do pOH. That might be easiest. Let's go opposite log of the hydroxide. 0.0125. To get a pOH of about 1.9. And then we can just subtract that from 14 to get a pH of about 12.1. And I can go look back at this original graph, and I think that's about accurate. Let's see, 30 milliliters of base. Hey, not bad. Yeah, when the base is at 30 milliliters, the final pH really is like right around 12. So we've gone past the equivalence point. Now we have excess base.